All right, let's take a look at the inverse normal example that I left you with in the first part of this video. So we were going to find the number of years before replacement necessary for a specific brand of CD player, which is approximately normally distributed. So our x's are distributed normally with a mean of 9.4 years and a standard deviation of 4.2 years. So looking like this. So I've set it up here to show what we're looking for. We're looking for the cutoff periods, which this is a negative z on the left and a positive z on the right, that puts 17.5% in each tail. So these are the probabilities that I'm looking for. Well, because there's 17.5% in each tail, this is symmetric, and so it's going to be the same z value, positive or negative. So when I go to find my x's this time, I'm going to really be doing this. X is equal to 9.4, and then plus or minus, plus for the positive z and minus for the negative z, whatever that z value is that I'd find in just a second, times 4.2. So now I just need to go to my z-table. So we're going to go through and we're going to get to the z-table, and I'm going to look up something that's as close as possible to 0.175. So I see 17s way down here, and I see 1736 and 1762. Those are the closest ones I can find. So 1762, that one is 0.10012 off. So I'm going to write that over here, 0.0012 off. That one is 0.0012, nope, yes, 12 high. And the other one, 0.736, is 1736. That one is a little bit low, but it's low, let's see, 0.14. 0014. It's 0.0014 low. So this one is actually the closer one, the first one that I came across, the 0.1762. And so I'm going to use the z that's associated with that. That's negative 0.9, and then up here 3. So my z is approximately over on this side a negative 0.93. And then on the right side it would be a positive 0.93. And you see this plus negative minus here, that's going to accommodate the fact that I have one of each. So I'll go to my calculator here, and remember that I have a very simple calculator, so I'm just going to multiply my standard deviation by 0.93, and then I'm going to subtract my mean, which is, let's see, what was my mean again? I don't remember. My mean is 9.4. So 9.4 from that, and that's going to give me the negative of the value I really want. And so, oops, I didn't get that. It was 5494. So this value is 5494, 54, and 94 for my negative value. And my positive value, that one I have to do 0.93 times 4.2, and I want to add that, oops, I'm not really sure what I did there, 0.93 times 4.2, and I want to add that to my 4.9, right, 4.9, no, 9.4. And that's going to give me my other value, 13.306. 13.306. So this one over here, if I round it up, I'm going to be just a little bit too high, right? That's closer to the mean. So I'm going to say this one is approximately 5.4 years, and this one 13.3. If I go down, I'll be including too much area, so I would want to actually go up a little bit on this one. So this one would be approximately 13.4 years. So about 13.4 on one side and 5.4 on the other. And that would be the cutoff points that would put the highest 17% and the lowest 17%. Now let's go take a look at the next example here. My next example says that most exhibition shows open in the morning and close in the late evening. And a study of Sunday arrival time showed that the average arrival time was 3 hours and 48 minutes after the doors opened, with a standard deviation of about 52 minutes. So if we assume that arrival times have a normal distribution, then what time do the doors what time after the doors open will all but 10% of the people who are coming have arrived? So to do this one, the first thing I'm going to do, of course, is I'm going to say that my x's are approximately normally distributed, and my arrival time, I can't put it in hours and minutes. I have to have it in just one or the other. My standard deviation's in minutes, so this has to be in minutes. So I have 180 minutes in 3 hours plus 48. So 180 plus, plus the 48, and that gives me 228. So my mean is 228 minutes, and my standard deviation is 52 minutes. Now I could have gone for those in hours, but 52 minutes in hours just doesn't make sense because it's a decimal, so I want minutes here. Now it says for part A, I want the distribution such that the arrival time over here puts all but 10% in there. So this is 10% on this side, and all but the 10% have arrived. So the probability that a z is greater than this z over here is going to give me 0.1. So remember that this tail here is the same as this tail over here. So when I go to look this up, I'm really going to be looking up the probability that a z is less than a negative z is going to give me 0.1. But I'm going to realize that the z I need is actually a positive value because it's in the upper tail here. So let's go back to our handy dandy table and look up 0.1. So 0.1 is up in this area. So let's see, I'm going to get bigger there, 0.0. There's 0.0003 and then 0.0985. So this one is 3 10,000ths off, and this one is off by 1/10. Let's see, 0.015 off. So this one is much, much closer. So this value is a negative 1.28. So that's what I'm going to use. I'm going to use that my z is approximately, now remember, I want a positive one because I know I'm in the upper tail of that distribution. So now the x that I want is the mean, which is 228 minutes plus 1.28 times my 52-minute standard deviation. And now I can get my value. So my value here, go to my silly simple calculator here, and I have 28 multiplied by 52, and then I'm going, that doesn't seem right. Something must have been in my calculator. 28 times 52, oh, it was right. And then I'm going to add to that, and that's my 228, correct? Yes, 228. And, oops. You know, that wasn't correct. I had not 28, 1.28 times 52. And then to that, I'm going to add the 228 minutes. And there I have 294.56. So 294 point, and that was 56. And so again, if I round this to 290, if I went 294, that's closer to the mean, so that would include more area. So I'm actually going to want to include just a little bit less here. So I'm going to say that this is approximately 210 94.6 minutes if I want to go to tenths of minutes, which, you know, I usually do. So that's the approximation there. Now for part B, let's take a look at part B. Part B says that I have at what time after the doors open will only 15% of the people have arrived. So this time I want only 15%. So that's on this side of the distribution. So this time I have 0.15 here. So this time I'm looking for the probability that my z is less than a negative z is equal to approximately 0.15. So now let's go over to my table and look up 0.15. 0.15, right there I have the 1/5s, and right there I'm getting close. So this one is 0.0008 off and this is 0.0015 off. So this one that I have highlighted right here is closer. This is negative 1.04. So my negative z is negative 1.04. And then of course I have to unstandardize. So my x is equal to 228 plus my negative 1.04, and that 1.04 is going to get multiplied by my 52. And so that will be my value. So now let's go to calculate that. 1.04 times 52. And then I'm going to go ahead and subtract, because that's a negative, 228. So I'll get 173.92. So 73.92. Now again, remember that if I am getting, my mean is 228, 274, or 174 is further away from it, right? So I'm going to go ahead and I'm going to say that this is 174.0 minutes approximately, so that I don't include more area under there than I meant to. So 174 is approximately that amount of time. All right, now part C says what is the arrival time that represents the cutoff points for which the unusual amount or usual amount of people arrived. Okay, well, usual, remember, is standing for the two standard deviations. So 2 standard deviations, it would be very easy to find out what 2 standard deviations out are. We just multiply 2 times this and add it to this and subtract it from that, and that'll be the answer to that. So that's not inverse normal. All right, so this is going to conclude this lecture for this time. I have one more lecture that I'd like to give on inverse normal.